finish off today, starting with Vicky Hsu from UC Berkeley. She's done a lot of stuff with LIGO and the detectors, and I think using squeezing to increase the number of detections. You've also done some other stuff with what did you say? Dark matter, atom interferometry for gravity, and awesome stuff that hopefully we get time to talk to and think about. Let's get started. All right. Cheers. Thank you.
Okay, yep, there it is. Is it? Hi, is this working now? I just turned it on, like, you can hear it now.
Yeah.
Okay.
It's
Okay.
more for the recording.
Yeah. Okay.
In the room. You just have to make sure you're speaking into that for the recording.
Okay.
And then I just
Sounds
make sure
good.
the clicker is all set. So you want to see green on the clicker too.
Oh,
So
okay,
it's on.
cool. Okay, great. Thank you.
Uh-huh.
Yeah, I know setting things up as the first person is always like a little bit. Okay, cool. Yeah, hi everybody. So like Justin said, I'm Vicky. Thanks for being here on a Friday morning. Thanks for inviting me to talk about quantum sensing generally to more people than are just physicists. So what I've prepared for us from now until noon is roughly, I'm going to start by talking about how we use quantum optics in kind of the most textbook manner. Oh. Yes. You're good. Yeah, so so first I'll kind of just give some context and give some background. And what I really want to share with you in the first part of this morning is like, why is a different side of quantum sensing. I think yesterday we heard from the magnetometry folks, like different ways you can use quantum particles to do sensing. And when the LIGO detectors, the LIGO like laser interferometer gravitational wave observatories, we're really able to use techniques from quantum optics to do something that's like far beyond what right now can be done with only classical physics, if you exclude the fact that lasers are inherently quantum devices. So that's, in the broader context of things, kind of an interesting case. And like, why is quantum sensing interesting? It's because it really offers an opportunity that can't be achieved otherwise by any combination of just classical means. And I think that's very interesting for precision quantum sensing, that quantum mechanics can let us be more sensitive than without quantum mechanics. So we'll see how we get on with squeezing and with LIGO, and I'll set the stage for that a little bit. After that, we'll see how we get on with respect to the break. We can either keep going on quantum optics and squeezing, or we can switch gears into how to use atoms to measure gravity extremely precisely at the part per billion level. So we can kind of do a take your own adventure for the second part. In case it's interesting, more for kind of an audience here, I'm from California originally. I'm from the Bay Area. I did my bachelor's at UC Santa Barbara, so pretty close to here. And the two options I was considering for my bachelor's degree was basically Cal Poly, San Luis Obispo, or UC Santa Barbara. Those were kind of the two places. I don't know exactly how Cal Poly is counted in terms of the CSU system, but I think they're kind of much more similar to a CSU in some sense than a UC. So I think that, yeah, just for context in this crowd, I've always kind of been in the California public school system. For my PhD, I went to Berkeley, and that's where I worked on atom interferometry experimentally. And then for my postdoc, I recently just finished up at MIT in the LIGO laboratory there, working on commissioning this big new upgrade that I'm going to talk about for the squeeze light system to kind of do it in a more subtle, powerful way for our observatories. And literally just about 6 months ago, I started as an assistant professor back at Berkeley, working on a combination now of atom interferometry for gravitational physics, squeeze light quantum optics for gravitational wave astronomy, kind of the very, very far ends of the spectrum. I sort of am putting this under the umbrella of quantum interferometry for, in this context, a type of quantum sensing. So again, with laser interferometry, these are kind of like role reversals of how light and matter work to enable sensing. Right, a laser interferometer, you use physical objects, like you use mirrors, you use physical beam splitters, like what we saw in the quantum optics lab. You're using these real objects to steer and direct light and interfere laser light coherently. And what we do in terms of quantum mechanics there is that the quantum nature of light quantized into individual photons is our biggest noise source today for the LIGO interferometers. And so we're using techniques in quantum optics, engineering quantum correlations between these down-converted photon pairs to improve the sensitivity of laser interferometers. Atom interferometers are almost the exact reverse of that. For precision atom interferometers, we use laser-cooled atoms instead of single photons like you saw yesterday. Instead of a single wave packet of a photon, we use a single wave packet of a single laser-cooled atom. We cool down the atoms, delocalize them out to like 300 nanometers in terms of their de Broglie thermal wavelength, and that sort of replaces the single photons. You might ask, why would you use single cold atoms instead of single photons? And for gravitational physics, at least, the answer is pretty obvious, right? Because atoms weigh something. They weigh very little, but they still weigh something, and therefore they're falling. And so with atoms, we naturally have a source for our interferometer that constantly falls due to gravity. It therefore accumulates a path length difference that's always sensitive to gravity. And we can control atoms very, very well. And so, unlike a laser interferometer, we have physical mirrors directing them around. An atom interferometer, we use pulses of light to kick the atoms around using atomic transitions. So these are sort of the two sides. One of them, in an atom interferometer, it's a quantum kind of source that goes into the interferometer. And a laser interferometer, we're using quantum optics to engineer the vacuum state to make it more sensitive. So let me just kind of start here. Laser interferometry. There's a big whole list of what we can do. So if anything gets boring, also feel free to ask questions during the talk. If a part is boring or not that interesting, we can also just like zoom ahead. Very flexible, very happy to play this however people want. Let me just lay out a little bit the context here. We use a laser interferometer to detect gravitational waves. What are gravitational waves? That's a very interesting question. What can gravitational waves tell us about the universe that we could never see with light? Also very interesting. We'll talk about that. How does a laser interferometer allow us to trace out space-time to measure these gravitational waves coming by? Talk about that. Talk about, in terms of quantum sensing specifically, I think a really important part of sensing, of course, is like sensitivity. It's not just that a quantum object is the sensor itself, right? It's what is your signal that you're actually measuring in the real world? How does my sensor actually react to physical things that are really changing? And how can we optimize the sensing part to the signal part to maximize sensitivity to something like astrophysical observables? So that's how we operate an observatory, right? And then we'll talk about how quantum noise fits in that whole picture. And maybe let me just get a quick show of hands here. Like, how many people here are like engineers in some way? Okay, of the engineers, how many are like like software engineers, like on the software side? Okay, great. How many are on like the hardware electrical engineering side? Okay, great, okay. So you're like a software and hardware electrical computer engineering. RF, oh, okay, that's great. Okay, cool, okay. So for the non-engineers, how many are physics? All right. Materials, right? There's a few materials. Astrophysics. Great, okay. So we have one. How many are kind of experimental lab people? Oh, wow, okay. So we have quite a few experimental lab people. How many are kind of pen and paper math-only people? Oh, okay, you do some math. Okay, great. Oh, okay. Oh, yeah, do we have any mathematicians here? I think we had, okay, so we have a couple okay, so you're a mathematician, but also in the lab. Oh, rare, okay. Great, okay, cool, thank you. That just helps to give me a sense of who I'm talking to here. Because yeah, as you can imagine, this covers the LIGO detectors, a lot of things in physics, engineering, software. Yeah, oh, I forgot to ask, do we have any chemists here? Okay, a chemist. Okay, great, okay. Theoretical chemist, great, okay. Yeah, so we have a good variety of people. That's great. Yeah, so, in terms of the context, what are gravitational waves? This is sort of the type of stuff we would typically talk about in an introductory astronomy class. So I think most universities, there's usually kind of like Astro 101, Astro 1, that just lays out the life cycles of stars and things like that. And a lot of that conversation now, gravitational wave astronomy is starting to enter that conversation. And in terms of laser interferometry, this is just the principle of doing interferometric measurements. That's pretty ubiquitous, right? Across engineering, across optics, across methods and chemistry and everything in terms of sensing. And so that's kind of, in terms of the physics curriculum, I would say it lands within, maybe lower to upper division electromagnetism for laser interferometry. Yeah, and then quantum noise, I think, is the part where, for this workshop, it really gets into kind of stuff you would see in an upper division quantum mechanics class. So that's kind of the range of topics we'll cover today, ranging from intro astronomy to upper division quantum mechanics. And a lot of the nice thing about LIGO for a context like this is it's extremely textbook. Even in atom interferometry, a lot of our applications are very, very right by the book, which is kind of fun to see. So we'll start by talking about what gravitational waves are, and just again to say, how does quantum sensing play into this whole thing? We are forced to get into, I'm not sure if you would call it quantum sensing, I would maybe call it quantum enhanced classical sensing or something like that, but it falls into this umbrella of how do we use emerging techniques in quantum mechanics today in deployment. Like, what is the situation we're put into where this is a problem? And that situation for us in LIGO is when the signal is about the same scale, or really the best signals are even smaller than quantum vacuum fluctuations in the electromagnetic field. When your signal is smaller than that, you kind of have to get fancy with it to be able to achieve reasonable SNR and to discover really new signals of this type. So that's kind of the way in which we're forced into this. And I think a lot of sensing applications are at their best when they only turn to quantum engineering as their last resort, because that means they've actually made the best possible sensor and they're quantum enhancing it. And this is an XKCD I think of sometimes. There are 4 fundamental forces between particles, right? There's, let's just start with the most obvious ones. There's gravity. Things fall down, that's obvious. There's electromagnetism, so we have Wi-Fi, also relatively obvious. That's how we see starlight. Then there's the less obvious ones. There's the strong force that holds together a nucleus in like an atom, somewhat less obvious. There's the weak force, and that's, I'm not even sure how to explain that one. That's how particles like leptons and electrons and muons and things like that interact with one another. And so if you look at the relative strength here, the strong force, obviously very strong. Electromagnetic force, pretty strong. Weak force, relatively weak. But neither of those are in the same league as gravity, which is by far the weakest fundamental force, even though it's the most obvious to humans, probably. So, there's all these things. We understand a lot about these forces, even the relatively obscure ones like the strong force and the weak force. And at the end of the day, the one we basically understand the least in terms of our general centralized understanding of physics is how gravity integrates into that picture. And that's something that kind of I'll talk about a little bit from the quantum sensing side. Dan, I'm sure, will also talk about this. And so in the early 1920s, gravity evolved from kind of, well, gravity was actually a pretty well-evolved theory even before the onset of general relativity. But there were really key things that kind of an apple falling down, 2 objects attracting each other with GMM over r squared, that basic Newtonian gravity had a hard time explaining. One of these things is, for example, space-time. And there's kind of this famous quote that space-time tells matter how to move, and matter, the energy density within it, is like a dent into this cloth that is the fabric of space-time, and light only ever traces out kind of the shortest possible path in this floppy bed sheet that is existence, I guess, of space-time. So one way you can think about this is like, we have space-time there. Again, you see heavy objects deform space-time, right? So what does light do? Light is our tracer of what is a unit of distance in space-time. So if you have something like the sun deforming space-time, what's the fastest path for light to take between opposite sides of the sun? It's not going to go right through the sun. It would fall into this big well, and actually that would take light much longer to travel that way. So what does light do? It goes around. That is something that's very hard for Newtonian gravity to explain. How when you deform space-time, how does light travel? And so this is sort of, at least in terms of the conception of general relativity, how you can imagine how it really starts to deviate from Newtonian gravity. In terms of, you talk about space-time and light as the tracer of the metric that traces paths. Yeah, and that, of course, that matter deforms space-time. We'll talk just a little bit about gravitational waves here. Let's see, does this play at all? Perhaps. Okay, so this is a slide that my grad student made. And of course, it has Kip Thorne getting stretched and strained. So what are gravitational waves? If we live in a relatively basic space-time, you have kind of that metric, the -1111 of basic space-time metric. And what gravitational waves do is they stretch to orthogonal degrees of freedom like this. What that creates is what, in daily life we'd call a strain. So gravitational waves create a strain into space-time. Again, you see the h bar, that's the amplitude of the strain. The 1 means that one direction grows as the other direction shrinks. That's how we see strain in terms of an L-shaped thing. That strain is proportional to like how far apart are the two objects that are producing gravitational waves. But in the end, if it amounts to that, if you calculate this for, say, a pair of black holes and a reasonable radius that we think is between them, this is when they do the initial calculations for, what is a source of gravitational waves. I could even imagine, what about black holes? You would see that you need to sense a strain of about 10 to the -21. If you had a roughly 1-2 meter baseline, like the height of a person, that would be sensing a displacement of 10 to the -21 meters. That's extremely hard. And so the way that big laser interferometers operate is basically increasing the baseline such that it relaxes the requirement on delta L, the actual distance change that you need to sense. And I'll have more about that later. The slides are actually a little bit out of order here. But what it amounts to is that, if you see the original papers from general relativity, it was like, of course, accelerating masses in general relativity will produce gravitational waves. But anyway, you calculate those numbers like 100 years ago, it seems that this was an effect way too small to measure. And so people were not really sure if it works. And again, you can kind of see here how two masses close to each other, they orbit. That orbiting, because the masses are very heavy, creates these ripples in space-time, especially as they come closer and closer and merge. And I'll show that more. So today, gravitational waves are basically a thing now. Gravitational wave astronomy is a thing now. The LIGO detectors made the first detection back in it was September of 2014. So 2015. So it's almost about to be 10 years since the first detection, which is very exciting for us. I'm sorry, these slides are slightly out of order. Let me actually go, okay, no, we'll do this. So this is an extremely exaggerated video of what it would look like for gravitational waves at an extreme scale to pass through Earth. Obviously, this does not happen, or else Earth would probably collapse and the universe would not be the way it is, right? But what you basically see, let me see if I have a better video later on, but the essential effect is this, right? That you have something, these masses somewhere in the universe are kind of in spiral orbiting into each other. That produces gravitational waves. As gravitational waves travel through space, they come through Earth, and you can see how it stresses and strains Earth like this in an L-shaped fashion. So the way the LIGO detectors operate is we have two L-shaped Michelson interferometers, exactly like what you kind of see there, but very unlike that in very important ways. But it's the basic concept, right, of a pair of L-shaped arms of a laser interferometer. And we've parked that on two opposite corners of the US. So one is in Livingston, Louisiana. The other site is in Hanford, Washington by Pacific Northwest National Lab. The Livingston site is about an hour north of New Orleans. And so the strain that we're measuring today, again, I talked about that baseline. So the arm lengths in our detectors are 4 kilometers. Next to the arms, there's a small service road. It's about a 15-minute drive on a small service road to go the length of one arm. We have 2 arms in 2 locations in the US. And the displacement that we're measuring, like this is very not to scale, right? So the actual displacement we're measuring is about 10 to the minus 18 meters of displacement on top of a baseline of 4 kilometers. So that's saying a 15-minute drive changed by a fraction of the radius of a proton is what that amounts to in terms of the precision that we're getting there. And so let me back up a little bit and say a bit more about gravitational wave astronomy before I delve more into the quantum sensing side, just because I think the context is really interesting here. I don't know how familiar people are with traditional astronomy, but I would say traditional astronomy is like telescopes. I'm sure people have heard of telescopes. What do telescopes do? And in fact, if you think back, like essentially most of human history, how do we observe the universe? How do we observe stars? How do we know what is like kind of out there? Typically, the main thing we observe is starlight, right? That's just electromagnetic radiation from distant stars. You might ask, like, can we just observe out into the beginning of the universe with starlight? How far can we really go with starlight? Starlight is hard as you're only observable in some ways, because light, as we talked about before, it interacts very strongly. A big problem for telescopes is things like dust in the interstellar medium. So if your only medium is starlight, which is what it has been for almost all of human history, light is very interactive. Every time it goes past an atom, it'll interact, it gets absorbed, it gets re-emitted, it gets distorted. And so to have the messenger of really distant information in the universe come to Earth after having interacted with all the intervening stuff, you see a very distorted picture of the far universe. This is kind of in total contrast to gravitational waves, right? Like gravitational waves on Earth barely interact and we can barely measure them. But that also means that they are a very, very clear messenger of distant astrophysics in our universe, because gravitational waves can pass through galaxies almost completely unperturbed. And that means that we can see way beyond the limits of dust if we can measure gravitational waves from farther and farther away sources. And it's also just inherently different, right? So this is a little bit the life of dust and stars and stuff in our universe from an intro astronomy class. So the way stars form is that you have a bunch of dust. That dust amasses more dust. Eventually, so much dust is amassed that you have a stellar cloud, and you start to get little points of collapse that form stars. If those collapse into relatively large stars, then you're on this bottom path over here. You have a big star. It basically explodes. If the mass is bigger than 3 or 4 solar masses, it'll collapse directly into a black hole. If it's more like 1 to 3 solar masses, 1 to 2 really solar masses, it'll collapse into a neutron star at that point. And so these final products of big stars, they don't, in general, really emit light. Especially a black hole, in general, does not emit light. And we can, if anyone's curious why we have photos of black holes, we can talk about that later. But in general, these are like totally dark objects. And the only way we definitely know that black holes, roughly the size of planets, exist is that we see the light from stars behind them get lensed by them. And that's how we know that they exist. The way that we know black holes are the hearts of galaxies is that we see black holes tearing apart all the stuff, and all that stuff is exploding and giving off light. And that is the way in which we typically see either huge black holes, like supermassive ones that create galaxies, or that we see relatively small ones is through lensing indirectly. But in general, these kind of we call this kind of the stellar graveyard, because stars have their whole life, they have all their stuff, and then they die at the end. And once they die, typically they kind of go dark to electromagnetic telescopes and things like that, because they don't inherently radiate. There's this NASA video of an explosion, in case that's fun. But this is roughly somebody's conception of what happens to stars when they die. A pretty typical thing that happens to stars when they die is that depending on their formation cycles, like why did it exist, how did it get to that mass, they may or may not have spin. Black holes may or may not have spin. depending on their formation channels. And these are all like very interesting questions we can ask about their lives and their formation by looking at the remnants. We can see, do the remnant black holes and neutron stars, do they spin? Do the black hole mergers we see have a line or anti-aligned spin? All of those things tell us about what was the life cycle of this star, this black hole in the universe. How did it collapse? What does the density look like out there? And so in terms of their remnants as black holes, oh, it's unfortunate that it's very bright and all gravitational wave things are dark. I think it's just the ambient lighting. It's just very hard. On that one, you can see it much better, actually. Yeah, on that one, you can see it. So like people have many different models of what happens for black holes. One model is that black holes are just kind of zipping around in our universe, and once in a while, they kind of randomly find each other, and then they catch each other gravitationally, and they in-spiral and merge, and then they explode into a final object. This is kind of that model of what happens. And these are essentially the signals that we detect, that big burst at the end. And so we can see with one more. And here I've just put up in the bottom left corner an L. So you can kind of see over here in the bottom left, what you see is that two black holes have caught each other. They're slowly in-spiraling and slowly merging into a final object right now. And if you look at how static a laser interferometer is compared to how the black holes are merging and sending ripples out into space-time, you can see that there's like a tension there, right? The fact that space is merging is going to stress and strain and differentially change what space-time, how space-time is defined for each arm of the interferometer. And again, that's the essential way in which we are really sensing gravitational waves. And you can kind of see what these chirp amplitudes look like here. They kind of in-spiraled in the beginning, and right as they collapse to a final object, the magnitude is very big. And so this was, again, in 2017, the Nobel Prize for the first direct detection of black holes. Okay, we can go through this a little bit more quickly. So the other product was neutron stars, of course. So neutron stars are actually like really awesome objects. If you've heard of pulsars, magnetars, these are all just spinning neutron stars or neutron stars with extremely high magnetic fields or things like that. Neutron stars are much smaller, much zippier. Again, the star's kind of small, it'll do that. That was a collision of a neutron star. The cool thing about neutron star collisions is that they can be very bright. Neutron stars are basically just neutrons and then gravity pulling them inward and the strong force pushing them outward. And so when a neutron star merges and explodes, again, a difference in electromagnetic versus gravitational wave telescopes is that once it becomes dark outside and normal telescopes can open their domes, then you can try to detect the light emitted in a neutron star merger. And that's very interesting. Yeah. So I don't know if this, just for scale, like a neutron star is about 1.5 solar masses, 1.5 times as heavy as the sun, fit within about 12-mile diameter. And it's extremely high density. This is not a meaningful number, but just to say a spoonful probably weighs as much as a mountain. And what you would get in that spoonful is just neutrons. So this is like a really interesting type of matter, actually, for nuclear physicists. It's very hard to find nuclear matter at this ultra-high density. Yeah. So, okay. Yep. Okay. And then, so this is sort of interesting. So when neutron stars merge, gravitational waves are in the audio band, so you'll often hear chirps. These are really light, so they have high frequency chirps. And then that's the gamma ray burst, detected exactly 2 seconds after basically the gravitational wave signal was detected. And so that's really cool because there's like literally a gamma ray satellite that detects it. The 2 LIGO detectors detect it. The Virgo detector in Italy also kind of detects it. Together you can do sky localization of the source. And then after that, what you can do is, again, once telescope domes close, you can start to point all your optical telescopes at that point that you found it in the sky. And you can see this transient blinking object here. So in time domain astrophysics, this is a big thing that they do. They look for transients in the sky. You may have heard of like the Vera Rubin Observatory coming online soon. This is also what Vera Rubin will do. You may have heard of the Sloan Digital Sky Survey, the LSST, Large Sky, forgetting all the adjectives, but some Large Sky Survey. They look for transient phenomena in space. And neutron star mergers, and the resulting kind of explosion around them are one source of transients that they can see, that we can see counterparts gravitationally, which is awesome. Yeah, so you can localize it, which constellation is it, the declination, the ascension. So you can really find this thing in a regular telescope, which is very cool. So then what we can do is full spectrum electromagnetic follow-up. So I know we had various people with various expertise in electromagnetism at various parts of the spectrum, right? So we first saw this thing in gravitational waves. That's that first chirp over there. And then you can see it in gamma ray telescopes that are flown, again, because there's too much absorption in the atmosphere, so those you have to fly in space. You can see it in the X-ray, and kind of once domes can close and stuff, so then you can kind of see it in the ultraviolet. You can see it in the visible, and the optical spectrum from kind of the infrared right through the visible. And you can see it in RF, in radio telescopes out a month later, still kind of blinking in that sense. So this is very cool, that we can detect from the same source the gravitational part and the full spectrum electromagnetic follow-up in this highly coordinated manner. It has never happened again since 2017. So this is something we're excited about, but it is very hard to do. But this is probably, for me, one of a very cool thing in physics, at least. And what do we learn? We learn that these collisions of neutron stars are one way that, I know we have some chemists, we have some material scientists, like one of the ways that heavy elements are forged in the universe is through the collisions of neutron stars, because then you have very high energy nuclear matter that's colliding, and that can kind of fuse up to these very heavy elements, and that's how they can be produced in the universe. What is the white? I think those are ones that cannot be produced naturally. Like those are like elements, I think berkelium or californium is maybe one of these ones, but that can't be naturally produced elements. Yeah, so this is just in terms of like, why do you do stuff like detect black holes and neutron stars? It's because in some sense it will really help us, doing fundamental physics will teach us a lot more than we know we were gonna learn maybe at first. And it teaches you a lot about where we came from. Just generally an interesting thing to do. Okay, so now we're gonna go back onto the quantum sensing track, but this is just some context of what you can do in some ways with gravitational wave astronomy. And these are kind of the first two really huge results that we had in terms of astrophysics. So again, like the scale that I was talking about, detecting these signals, it's a very, very small scale. It's a very small displacement change that we're measuring over such a huge baseline. So there's this other video. Again, it comes up much better on that TV. I'm sorry, I can go back a little bit here, and you can talk about how small really is 10 to the minus 18 meters of displacement. From an atom, you can zoom way in, way in, way into a proton. This is a proton's radius. And it's like, yeah, it's gonna do this. This is all the signal that colliding black holes in our universe, in our relatively local universe, can produce. And that's because gravity, again, it's so weak that even black holes 30 times the mass of our sun that collide with each other at a quarter of the speed of light, all they can do is this. This is why we are really stuck with the quantum sensing problem in some sense in the LIGO interferometers. This is a very, very small signal. It's less than 0.1% the radius of a proton over a 15-minute drive. That's how much we're detecting the two arm cavities changing by. It's a very small signal. And just to be very clear about it, like at this very extremely microscopic sub-proton level scale, quantum effects are much bigger than our signal. And so today you'll see quantum noise essentially is the biggest limiting and determining factor of how astrophysically sensitive we can be. So that's why it's cool to work on quantum sensing in a context like laser interferometry for astrophysics. Something that people have compared this to before as well, like it's hard to get a sense of like what is 10 to the minus 18 in terms of a distance, in terms of a precision. Another way to say it is like if the diameter of the Earth changed by an additional grain of sand on one side. That's also a similar distance scale to the type of precision sensing that we're talking about here for LIGO. Okay, so again, This is a very small absolute length change. What we want to measure, though, is not a length change, but a strain, because what we're really trying to measure is interferometric strain, right? So one way to amplify the strain you have is by amplifying the baseline to relax this. Again, we're measuring delta L over L, right? So if you increase L, you relax delta L that you must be measuring. That is why the LIGO detectors look like this. So this is an overhead drone view of the Hanford site. I remember you were working at PNNL before. You've probably seen this from the ground. It is a large distance. Even when you look at it from the ground, you can't really see the end stations unless you're, yeah, it's hard to see the end stations from the ground because it's both very flat and it's very far away. So just for context, when you go to work in the morning, you park your car. Can you see this? You park your car right over here. This is a parking lot for scale. Houses about, I don't know, 30 cars. You go into here. The lab is in this area. And you can kind of see where the arms of the interferometer are, right? If you have an L, beam splitter is not actually in the middle of the building, but we can kind of pretend it's in the middle of the building. That goes out to the X arm there and the Y arm over here. The light travels all the way to the end here. This final building houses essentially a single mirror. It comes all the way back. This is the mid station. This is 2 kilometers, about 1.5 miles, just over a mile, just around a mile. It comes back to here. They interfere. And then we detect that interference pattern as a power fluctuation on a photodetector. That's about right here. If we zoom in to like, what does that little building look like? This is the inside of that seemingly little building. So these are people here in comparison to our vacuum chambers. These are, you know, the Michelson interferometer in the quantum optics lab is a single, it's very small, you can see it all. We have to baffle everything because stray light is a huge problem for us. And so inside these big tubes, there's a laser beam that's kind of enclosed by these tubes here. So the tubes are about 2 meters in diameter. We operate one of the largest, maybe I think the second largest vacuum system on the planet. And the beam splitter is right about here. Huh? No, I think it's actually the NASA facility where they test rockets. That is actually very, very big. Apparently the LHC, I think we might be, if you count the 2 observatories together, it's bigger than the LHC because the LHC is a very narrow tube. We have a giant tube, so volume. They win in distance, but we win in volume. Yeah, so if you look like, you know, this is a super small like distance we're measuring, right? Like if you just walk by, generally that's a much bigger signal than any signal we could possibly measure from space. That's why we have quadruply suspended optics in vacuum. So these are suspended at the bottom stage of a quadruple pendulum. This is a very complicated thing. I'll just show you this photo of, it's very macroscopic. It's funny, but it takes really macroscopic stuff to measure really, really microscopic stuff. So just for the contrast there. And you can already see in terms of kind of, you know, I know you all are teaching many different classes and from many different fields. Just from this, I think you can maybe appreciate how many different fields of science and engineering come into this. So, you know, all of these suspensions, it's kind of the most textbook mechanical engineering problem you can define, right? I have a quadruple pendulum. Like, what is the vibration isolation and what do those springs for each of those pendulum stages need to be tuned at? What do the reaction masses have to be to achieve a given level of vibration immunity at a given frequency? So actually, most of the people who work on our suspensions, their background is in mechanical engineering. And we've done, LIGO's had many, many PhD students in mechanical engineering, both for vibrations, isolation, suspension design, even things like, this is the end of one cavity mirror. How can I translate this mirror without any pitch? That is currently one of our PhD students' PhD projects. How can I translate this thing within a cage that's fully suspended, like to change the length, but not have it tilt? So these are the sorts of, just like for context, right? This is not just a quantum sensing problem. This is much bigger than that in some sense. You can see there's tons of wires required. These are all have to be in vacuum hardware. You can see this, this optic here is one of our input test masses. So I'll show you in a bit, but one of our biggest issues where we actually have a lot of material scientists and condensed matter physicists in the LIGO collaboration is figuring out how to make the lowest noise mirror coating possibly achievable. We already have quite good ones. We need even better mirror coatings than we have now to reduce the thermal noise just within the mirror coating. Right now it's like this because there's first contact on there. That's just a layer to protect the optic when you do a vacuum incursion from dust. And so this is a pretty big thing. This is Betsy Weaver. She's our senior detector engineer at the Hanford site, and she was first a LIGO surf student. That was our summer intern program, like 20 years ago. She was like the very, very first summer intern we had, and she stuck it out her whole career. And she's going to stick it out her whole career if the NSF keeps funding us. So just like for context, people, a lot of the really, really senior people we've had in LIGO have come in as surf students. Maybe they've stuck around for a master's, maybe they've done a PhD at one of either Caltech or MIT who manage the observatories, or any institution within the LIGO scientific collaboration. So we have lots of PhD students from all non-LIGO lab institutions, for example, like, anywhere around the world. There's tons and tons of LIGO lab institutions. Yeah, so just in terms of like how a summer internship can become an entire career, we have many of those cases in LIGO where people like it as summer interns from any university, any college, and then yeah, they just stick it out, and in 20 years, they're the ones responsible for the input and the end test masses of our detectors. Oh, so yeah, I don't know what you call a LIGO person. I don't know. That's a good question. I don't know what we call ourselves. I think we just call ourselves LIGO people. But yeah, it's like, I think amongst our senior staff, probably like 30 to 40% of them were first surf students in college. They started with a college internship, they chose a LIGO institution for their PhD, or they just went directly into LIGO engineering after that, and that's been their entire 20 to 30-year career. And we've had people now already retiring from full careers from interns. So that's just for context in terms of, if you have students interested in astronomy but wanting to do, computer science, there's a lot of, I'll talk about it in a bit, like computer science involved. There's a lot of optics, a lot of engineering, a lot of mechanical engineering, electrical engineering, RF engineering, all sorts of engineering, and all sorts of science. You want to condense matter, whatever. Yeah.
So the surf program, just a little, is it through, like, does LIGO have its own surf program, or is it an NSF surf program?
It's an NSF-funded surf program administrated through Caltech, but it's not the same as the Caltech. I don't understand its relation to the Caltech physics surf program, but a lot of the HR for the LIGO observatories goes through Caltech, so that's how this is administrated. Yeah. But yeah, I think another thing to mention on this front is, so I don't see anybody I know from CSU Fullerton here, but CSU Fullerton has a very robust LIGO group. We have on-site operators that have come from doing a master's degree in the Fullerton group, and we have one of our scientists that we just hired at the sites. She did her master's as well, and then did her PhD at Syracuse, and now she's a detector scientist at one of the sites. But yeah, a lot of people in LIGO have actually come through the CSU Fullerton Gravitational Wave Center. Yeah, so there is a big presence from the CSU system and an increasing presence from the UC system within the gravitational wave astronomy generally. So that's kind of an interesting thing. Okay, a little bit more on the science side here. So there's a lot of different things we measured. I told you that we measured like these merging black holes, these merging neutron stars. I would classify those in this compact binary inspiral. And so there's a lot of things you could be measuring with gravitational wave detectors, right? We measure relatively fast, so I showed you the videos of black holes merging. That took a total of 1/4 of a second. The black hole kind of merges that signal, zips by the detectors, and that's it. So you have to be operating with the maximum duty cycle you can to catch whatever comes by, because when these signals come by, they're 1/4 of a second. They're fast. And these, we can detect them in low latency very quickly. Like we can know that we've detected something within, I don't know, 30 seconds, we'll know. And I will get a text alert within 5 minutes of what we've detected and what our low latency parameter estimation thinks that it is. And we can do that because these signals are well modeled in general relativity. So you numerically solve the equations of general relativity for black holes of this mass, this distance apart, this distance away. I'll show that in a second. And then you can see, oh, okay, I probably most likely detected something like this. And exactly, those are short duration, well-modeled signals. There's all the other combinations, right? There are well-modeled signals that are long duration. Long duration as in, just imagine that you had one of these short duration signals, but of super heavy black holes that would make it go very, very, very slowly. You would never see it chirp because the time it would take to chirp would be like half the age of the universe. Or it might be a year. It might be even, it could be a very long time. So sometimes you can imagine a continuous wave source of gravitational waves might be something like a neutron star with a small hill on it. People look for things like that. Right now, we think a neutron star can't have a hill bigger than a millimeter. And how do we know that? You can kind of look at what are the nuclear equations of state for very, very dense nuclear matter. It should be a perfectly symmetric scenario, right? It's just strong force and gravity. There should be no asymmetries that lead to something like a hill. But if there was something like a hill, we could potentially, see this like continuous wave, because then you have an asymmetric object rotating quickly that is deforming space-time and sending out these continuous ripples, and we could detect something like that. There's more interesting stuff on that later, but just imagine this scenario here going on forever and ever and ever. That would be continuous waves. Then there's like the exciting but exploratory physics, let's say, of what could we see. Something that we could see is if we were more sensitive, we could see a star that goes supernova, implodes into a core collapse supernova, and that explodes. We could see that explosion as a short burst. However, there's not great models, so that is exploratory, right? Because we don't exactly know how general relativity, how a supernova collapse will look like in general relativity in terms of the gravitational waves that we'll produce. So there's a lot of modeling going on to understand what would that even look like in our detectors. And then there's possibly there's many versions of this, but let me just talk about one example really quick, which is a stochastic background of gravitational waves. Imagine in the optimistic future that we are so sensitive, we catch every single black hole merger ever happening. Then we would just see like an infinite superposition of these bursts, and we wouldn't be able to tease any of them apart, right? Because we see so many. That would lead to a stochastic background of gravitational waves. Unfortunately, for real detectors, that is hard to distinguish from random noise in your detectors. So this is a hard signal to both model and to look for. And then another really interesting thing that I think is really the holy grail of all of gravitational wave astrophysics is to look before the Big Bang, right? Because I don't know if people have heard of like the cosmic microwave background. Have people heard of this generally? Yeah, of course, RF people will probably know the cosmic microwave background. So the cosmic microwave background, do you know what it's from? Do you know what it is?
Leftover from the Big Bang.
Yeah, exactly. It's leftover from the Big Bang. Actually, what it is, it's a leftover from the Big Bang, but it's really like that photons from earlier were just so busy scattering from how dense the universe was in the early universe that photons couldn't actually escape then. So about 400,000, let's say 380,000 years after the Big Bang, this is the current kind of thinking. About 380,000 years after the Big Bang, then basically reionization happened, and then photons could finally like kind of leave, because before that they were stuck in this hot quark gluon plasma where photons were just kind of bouncing around forever, and they couldn't travel an appreciable distance before scattering off something else in the early universe, because the early universe was a very high density. But that is the time period, in the very early universe, what happens? Inflation. Universe gets really big. Something like that produces gravitational waves. We won't see that directly in photons because the photons are so busy scattering during that time that they can't actually travel away from then. And so kind of the signature that we see from the early universe is the cosmic microwave background. That's the leftover imprint of photons scattering off this hot gas. And you can do indirect searches for kind of pre-Big Bang, pre-cosmic microwave background signals in terms of the imprint, like the B-mode imprints that are left by inflation onto the cosmic microwave background. But gravitational waves are not subject to scattering from this quark-gluon hot plasma in the early universe. So you could actually potentially get gravitational waves that go right through all that plasma and still reach us today. And that would be like the most amazing thing you could ever imagine seeing, is a real direct signature from pre-cosmic microwave background, because that's not easily observable in anything but gravitational waves and possibly neutrinos. Yeah.
Does that also, so like the reason the microwave background is in the microwave
Yeah.
is that, you know, it was
Yes.
in the
Hot.
X-ray or
Right.
something when,
And then,
when it initiated, and then
yeah.
has basically redshifted as
Yes.
the universe expanded. Does the same thing happen to the gravitational waves?
I have no idea.
Yeah.
I have no idea. I think it does. Yes.
It's at 1 Kelvin.
So, okay.
Great calculation in Kelvin terms.
Yes. Thank you. Yes. It is a thing that people are working very hard on right now, are very interested in trying to understand, like, how could you get a definitive signature? Because again, in terms of like always linking this back to experiment, right? Like, what we look for as experimentalists are waveforms. The waveform from a stochastic source, whether it's inflationary gravitational waves, whether it's just stochastic background of stellar mass binaries that are merging, supermassive binaries, whatever is creating this background, you have to be able to know what that looks like. And you have to be able to distinguish that from your detector noise. And how will you distinguish noise from noise? This is the ultimate problem in trying to understand, like your question, like exactly what would it look like at different frequencies of gravitational waves? Because there are many different detectors coming online in the future soon, looking for things. Okay, this is just a more clear thing into how do we know what just came by? We can only do this again for well-modeled waveforms that we know and understand, right? So the parameters that's gonna change in this video are the distance, like how far away, and just for context, from us to Andromeda, the next nearest galaxy, it's like a megaparsec, roughly. Like the size of the local group, which is like 80 to 100 galaxy clusters, is like 50 megaparsecs, right? So like starting with a number like 800 megaparsecs, that's about maybe 7 to 9 billion light years away. This is already a very far away signal for an optical or electromagnetic telescope to see. This is very far. But in gravitational waves, it's not far. So you can see what happens. You know, we'll tune the distance, we'll tune the mass, and then several other things. So as if the source is closer to us, signal amplitude gets bigger. If it's heavier, these things move more slowly. If it's lighter, moves more quickly, right? Okay, the total mass of the detector is not equally sensitive to displacement at all frequencies. And then we find the final best fit waveform. And this is how we can know within like seconds, basically, what just came by our detectors, what just happened in the universe. This is obviously a huge computer science task to do low latency parameter estimation for waveforms from general relativity. But this is actually something that the Fullerton group is like very, very involved in, which is just cool because it comes out of the CSU, a lot of it comes from the CSU systems. Okay, so with that, what do we see? So in the first 3 runs, what we see is this. You know, you see the biggest neutron star, the smallest black holes kind of in this region. So these are kind of neutron stars and black holes over here that we've detected with optical telescopes, again, indirectly. With the LIGO detectors, we've seen all of these things in blue up here. And what you can see is that, like, basically before we had gravitational wave detectors, we just didn't see any of this stuff. We didn't see that there are just like black holes that are 200 times as heavy as our sun, just floating around in outer space. We never saw them before because they're dark. And now that we can see dark things, we can see that there's all this stuff that's been out there the whole time. Again, down here, there's not really any scale to this plot other than mass goes up in X and Y. But you know, there is a big difference in the black holes and the objects that we're seeing electromagnetically versus gravitationally, which is pretty cool. Okay, I'm gonna go fast through this part of what is a laser interferometer, but I think Chad already talked about this probably on day 1. As an aside, lasers are inherently quantum. And some people talk about quantum, like the first quantum revolution, the second quantum revolution, quantum 1.0, quantum 2.0, where the first one was kind of using quantum mechanics to make new cool devices. And again, the second quantum one, we're really using subtle tricks like entanglement to enhance devices or create new functionalities of devices in some way. But yeah, don't want to discount that, you know, lasers are inherently a quantum thing. For example, the Michelson interferometer. So here, what you can see is just a diagram of a Michelson interferometer. For us, we send in about 60 watts of laser power here. You can see these arm length movements. That's the differential displacement of the arms, delta L. This baseline here is, oh yeah, right. So then the arm length changes. They're transduced into power fluctuations on a photodetector here. That's how we ultimately detect things. We reduce arm length change to power on photodetector. And what we're detecting is power on photodetector. So we're looking at a delta L of, you know, again, order 10 to the minus 18 meters here on this baseline of 4 kilometers to get that 10 to the minus 21 strain sensing number. Yeah.
So there's no way to aim LIGO or anything, right?
No.
You're just looking where you're looking, right? There's no ability to.
Right. LIGO is much more, it's less like an optical telescope where you have pointing and more like a radio telescope array where you just have a flat antenna pattern. Well, not flat, but you have, essentially you define an antenna pattern with how you install it. So the two LIGO detectors are actually in opposite cardinal directions for this, right? Which gives up some sensitivity, but it allows for localization. So we take an intentional hit. And one way they used to talk about LIGO is as gravitational wave antennas. Maybe that's like a more, a different way to think about it than an observatory. Observatory is pointing, right? Antennas are just there. It's much more like an antenna.
And is there some concept of how focused it is? Like in the sense of that, like, are
Yeah.
you really getting some gravity waves that are like coming in at some angle?
Yes, you can get them from any angle. Yes, you can get it from absolutely any angle. Yeah, so like the sites can't be focused. And so that's why you have like this whole network all around the world. So we have sites in like, not we as in LIGO, but the gravitational wave detector network. There's an observatory in Italy, the European Observatory. It's about an hour north of Pisa. There's an observatory in the bottom of a mine in northern Japan whose sensitivity is kind of coming up. And there's actually been funding approved now, and things are sort of getting underway and whatever that means in this environment for LIGO India as well. So there is an Indian detector coming up that's part of the NSF LIGO network of observatories. Yeah, the detectors don't move, but we add more and more detectors on Earth in varying orientations to try to be able to do triangulation with a static antenna pattern. That's like the framework it fits into. Yeah, that's okay. What we look at for localization is the relative time delay between observatories. And that's how we triangulate, and then we send out, and NASA sends out these GCN circulars whenever there's a transient event detected. So when we do sky localization, that's how we find the source, is based on the relative time delay between observatories. Yeah, so then again with this laser interferometer, I won't go too far into it. So this is just saying again that the power fluctuations, and the reason why laser interferometry is powerful, just to say it again, is because we can get fully from, you can see here, the power at the output port can go from fully bright to fully dark if the length change is like a quarter of a laser wavelength. And so for a 1 micron laser wavelength, you can go from fully bright to fully dark with like a 250 nanometer change of the arms. Right? And so that's where you get, in precision measurement, what we talk about is the scale factor that you leverage for precision, right? That's where we get the scale factor from, because you're interfering two coherent laser beams, and within a fraction of the wavelength, that length mismatch produces huge power fluctuations at the output of the interferometer. At least that's how we configure LIGO. So then what we reduce the problem into is, oh, sorry, I didn't realize that's a video. Anyways, so what we reduce the problem into is, again, we're not, how do you get such sensitivity on a displacement? We convert it to laser power on a photodetector, and then we add a lot of photons so that even a small change produces still a measurable power change at the photodetector. If you think about what is laser power in general, what is a watt? It's energy per second, right? That roughly translates into photons per second. And that's how we face a limit of photon counting and timing noise, because what we're measuring is photons per second, right? And so the question for quantum sensing is, how do we get more information per photon per second, in some sense? And I'll add as a caveat to that, like, how do we do this? In some sense, trying to get more information per photon per second is a statement that we want to measure more strongly. In quantum mechanics, every time you measure more strongly, you also have more measurement back action. We want to measure more strongly, but also not have consequences like back action from increasing measurement strength. And this is kind of the crux of the quantum measurement problem that I think LIGO set forth decades ago. Yeah, just kind of an interesting perspective on that maybe. There's a lot of tricks that we have played over the years. The most basic trick is that we don't just have, like you see in the quantum optics lab, arms. We actually have arm cavities. That allows us to circulate a lot of power because they're resonantly enhancing the power in the arms. We get actually a huge factor of that. We're circulating, for 60 watts input power, we're circulating about 400 kilowatts today in our 2 arms of our observatories of CW laser power at a micron. So this is a very high power laser operation. It's a little more complicated than even just arm cavities. What we really have is we have power recycling and signal recycling, because in order to get the power enhancement, we have to cut the bandwidth, but then we cut the bandwidth so much we can't detect gravitational waves. So we had to increase the bandwidth after cutting the bandwidth for power enhancement. That's why we have signal recycling. Of course, if you're operating the arm length such that you get destructive interference at the output port, that means that you get constructive interference at the input port. That means all the power is coming back out the input that you send in. So we have power recycling to recycle that back. And then really what we do in quantum sensing for LIGO now is engineering not kind of the bright state and how we do high power operation, but we engineer on the dark state at the output port. We're measuring, the light at the output port, and so we actually need to measure that light, not beating with standard vacuum fluctuations, but beating with squeezed vacuum fluctations. So that's sort of the principle of squeezing. And this is even just a high-level CAD drawing, but just to show you our core optics are pretty complicated at this point. And you can see that this is really like in terms of engineering, again, like LIGO is a big physics experiment in principle and concept, but what it really comes down to is a lot of engineering at all levels with all skill sets. Okay, I'm not gonna play too much of this drone flyby of, this is, I guess, the Hanford site. But yeah, just to give you a sense that this is really a facility scale operation. And there's, and for this, for a teaching setting, it's just like, this is the Louisiana site. There's a lot of skill sets that we need in LIGO. Because you want locations that are as far apart as possible in the US. So right now there's about a 10 millisecond light travel time between Louisiana and there. And you also this is a big political funding budget item. So it can't be in California and Maine or something like that. Can't be like in Boston, and can't be at MIT and Caltech, right? So, and
You also want to avoid traffic.
Yeah, you don't want.
To the fly.
Yes, yeah, you want a place with not many people that you could get bipartisan support for as a line item, and various things. Yeah, there's reasons. Yeah. There are proposals for a third generation of gravitational wave detectors. Talk about that in a bit. But the next generation, again, this idea of it's hard to do better actual displacement sensing, right? So what can we do? We can increase the baseline to get better strain sensitivity for the same length change. So the next generation we're proposing is 40 kilometers, not 4 kilometers. So we're looking for a site now for, right now that is in site selection phase. Indiana is hard because there's a lot of, for a 40 kilometer site, you need a big empty space. New Mexico, Utah. These are places that have big empty spaces without like once in a while a highway, a little town, like a, or like a clearing, right? You're gonna build, you know, if you have two 40-kilometer arms, this is like a 20 by 20 mile clear empty zone. Ideally, it has a slight valley that counteracts the Earth's bulge. Like there's some things you could want in this. So there's yeah. So these are kind of here. The rest of the world, you know, a lot of sites kind of slowly coming up. Right, so okay, we'll just keep going. So this is for laser interferometry. So what we really want to do is we want to consider the signal and the noise, right? So we've talked about like different types of signals, why signals are interesting, things like this, but it's very important to consider what do these waveforms literally look like? How do we design hardware to match astrophysical objects that we want to observe? So again, like heavy black holes that are relatively close by, you can see the amplitude, the frequency, all of that information is encoded into these waveforms. Oh, I'll show you that in a bit, in like 1 second. But the main thing I want to show you here is that binary neutron star signals go on for a long time versus, for example, black hole signals go on for often fractions of a second. So what we're looking for is operating a continuous laser interferometer with high duty cycle to capture signals that come by for a split second. That's kind of the way that we're operating this. And like coming from atomic physics is a totally different background, because atomic physics is based on techniques that are like have pulse sequences, right? Anytime you have, like, that's not a continuous sensor in some sense, because you're taking the average through a pulse sequence measurement, and that is your discrete measurement in that time interval. So laser interferometers kind of do a cool thing in that sense of being a really continuous measurement, so that we can look for these fast kind of signals that come by. Neutron stars go on for a long time in our detection band. They go on for many seconds. Okay, so this is now the most important part of mapping all the cool things you actually want to sense into detector hardware, right? And for quantum sensing, again, I think this is like the most important thing, is understanding your signal, really. So, you know, we looked at the in spiral. That's when they first catch each other. They kind of come by. That happens, you know, kind of in the 10 to 100 hertz range for objects that are, you know, tens of solar masses, right? For very heavy objects, they move very slowly. Most of their signal is actually outside, a little bit too low for the LIGO band. That scales, if you think about galaxy mergers, those supermassive black holes will merge in the LISA band for future space missions that will do gravitational wave detection in space telescopes. Yeah, so the heavier objects kind of bottom out, too low frequency for us to detect on Earth due to seismic noise on Earth. But small signals, lighter objects will go on for longer times. But you can see really the crux of like where we need to be the most sensitive is about 100 hertz. That is the point where there is the most science for us to gain, like per noise. So this is really the frequency that we want to maximize things at. So you can see the merger, the rain down, or these sorts of phases. We can learn all sorts of different stuff by detecting this waveform with very high SNR. You can see this waveform chirps through frequencies, right? That's why we quote here. I'll show you a lot of these noise things. What this is telling you is this is how much noise we have at a given frequency per second. That's why it's quoted per root hertz, because the waveforms move fast, and so we can only quote our noise per root hertz at a given second, because it's always real-time sensing, right? So that's how you'll see these plots as a function of frequency. What is our noise? And so most important thing to point out is that if this black curve, which is the detector noise spectrum, is higher, that means there's more noise per frequency. We're less sensitive. If it's lower, there's less noise per frequency. We're more sensitive. Yeah.
Is that 60 cycle noise?
That is, so this is a spectrum actually with the noise removed, with the 60 hertz removed. So here, that is not the 60 hertz spike. That is probably some like HVAC, where the motors are getting coupled in, because you can see actually here, this is the first peak from the HVAC, and this is its harmonic. The 60 hertz spikes are like this, where they're very, they're clean. They're very clean. This broadening is from acoustic stuff, pump stuff. That's why I was very interested in all the questions yesterday of where all the noise comes from. We spent a lot of time looking at this plot. Yeah, so here's kind of how you can see the signals compared to the noise, and the game that we want to play is this, like how we quote signal to noise ratio, right? It's the ratio, for example, this blue line compared to where the black line is. That's our SNR at a given frequency. So that's how we talk about sensitivity in terms of signal to noise ratio. Just to spell that out very, very clearly. This is what it means. And again, this is how much noise we have. So if there's more noise, black line is higher. Less noise, black line's lower. If you look at like, why is our noise there and not infinitely low? What limits the noise? So the way we talk about that is in terms of a noise budget. We say like, what are the key parameters of our system? And what are the corresponding noises in units of this strain noise, right? So the black here is the total noise. It's very hard to see, but you can kind of just see it clearing it here. The purple here is quantum noise. And that's the problem that we're really trying to address. You can see that most of the noise we measure in black is limited, just defined by the purple, which is quantum noise. Except right around this really super critical region, like we talked about, 100 hertz, there it's a mix of quantum and thermal noise. For the material scientist, that really is the Brownian motion of the atoms in the mirror coatings, because that is not the same across 4 different mirrors that we're probing as our measure of strain. The different interferometer mirrors can't have correlated Brownian noise fluctuations in their mirror coatings. That's the noise we're measuring at 100 hertz. Okay, that is actually basically what we measure. So this is if you compare our sensitivities in the current observing run for the 2 sites, the red and the blue for Hanford and Livingston, and you plot those kind of major noise sources at low frequencies, controls noise, seismic noise, random garbage noise. This purple noise is quantum noise. You can see it limits, it's a big factor across most of the band, and we're still always working on getting more and more quantum limited. That is another statement that's important to say for quantum sensing. If you really want to do quantum sensing, you have to remove all the classical noise such that you're only limited by quantum noise, then you engineer on the quantum noise, right? That's how we have to do it in LIGO, because we're not interested in just studying quantum mechanics. We're interested in like performance and sensitivity, right? To actually get an application where the quantum enhanced version outcompetes a classical version, you have to already be operating the best classical sensor possible, right? That's operating a quantum noise limited sensor. Then you apply quantum engineering, you lower the quantum noise floor, and your whole detector noise floor lowers correspondingly. So that's what we do in LIGO. And now we're starting to lower it below the limit of thermal Brownian noise. Okay, we're gonna go a little bit through here. Finally getting to quantum noise. So one way we could do this is take the break and then come back to this for part 2. Or we can rush through this. We can take the break maybe and come back to this, unless we can go through a quick, maybe we can go through 2 slides to introduce it, and then we can break in like 5 minutes. Okay. That way there's some context for the next part. Yeah, so quantum noise is basically, quantum noise creates 2 problems to be solved. And we engineer the correlations in photons, so engineering quantum states in light, and that's how we solve the problem of quantum noise. So just to go very quickly here, just to introduce this concept, which probably doesn't need much introduction, like in the electromagnetic field, there's 2 quadratures, amplitude and phase. If you talk about the electromagnetic field in the photon picture, there's kind of 2 quadratures again. There's the position of the photon and the momentum of the photon. It doesn't really matter what orthogonal basis, what you call your axes there. Just position and momentum, or cosine and sine quadratures of the electromagnetic field. Both are very valid ways to say it. But the key point is that because these are non-commuting operators, meaning that these operators are correlated, so they impact one another, if you consider it a perfectly dark, empty box, like anywhere in the universe, there is going to be, on average, half a photon in that box, because the vacuum state has 0 or 1 photons, and you randomly have photons popping in and out of the electromagnetic vacuum state, such that time average in any measurement interval, you have about half a photon of noise. That's 0-point energy. Another way to say this is you can't know exactly where a photon is at any given moment. That imprecision is another statement of 0-point energy, generally speaking. Engineers probably hear this a lot in terms of shot noise, photon shot noise. And we'll just say like this, you know, there's always photons at any given time, anywhere on a fringe, just popping in and out of existence in the vacuum state. That's vacuum fluctuations. Right. And what this means for metrology is that we can't measure X or P with arbitrary precision at the same time, because X and P are correlated variables. And that actually means that measuring X or P too well will make the other uncertain. You'll increase uncertainty in the conjugate one by measuring one of these parameters too well. Yeah.
Why is that you identify photon position with field phase as opposed to the square of the field and we give you the intensity?
So in terms of like the vacuum state, I think it's easiest to talk about the field versus the intensity. Is that the question? Yes. It's easier to talk about that. Why? So, okay, maybe I'll say at least you could absolutely talk about it that way, but for our purposes for squeezing, we'll get into this after the break, but the type of squeezing we do is we're squeezing the noise in one quadrature of the field, which creates noise in the opposite quadrature of the field. And so for that purpose, typically when we talk about squeezing, if you were to do it in like the Hamiltonian formulation, which maybe because you're a chemist, you're familiar with that, typically what you would do is you would quantize the electromagnetic field into its field operators, and you would apply the squeeze operators there. And so that's how we see what we call quadrature squeezing, squeezing of one noise in one quadrature compared to noise in the other quadrature. And so for that discussion, it's sometimes helpful to have that in the field picture because you're talking about quadrature squeezing. There are,
For an electron, of course, that's obvious because in
Yeah.
the case of an electron, the electron has a mass.
Yeah.
Photons do not have
Yes.
mass.
yes.
So,
But photons don't have rest in that
very
way.
easy connecting to the momentum.
Exactly, yes. And that is an important point for later, where a big noise problem, if you talk about how do, like, okay, there's these two quadrature of the fields. In LIGO, these two actually manifest as two very, very observable noise sources in their own right. Because what actually happens is we sense the photon recoil from squeezed light. So for that discussion, it's easy to think about it in terms of a photon kicks a mirror mechanically recoils from the photon kick. And so in that sense, it's helpful to think about it as photons and their position and momentum, because you want to think about timing fluctuations in terms of photon counting in terms of shot noise, and you also want to think about the mechanical back action of a photon hitting a floppy mirror. I don't know if that's helpful, but I think there are many ways you can talk about it. Yeah.
I don't know if this will be helpful or not.
Yeah.
But, the way I justify thinking about this in terms of field quadratures is that fundamentally what you're going to do is you're going to do an interference measurement. At the end, you're going to add fields together
Yes.
and then take the amplitude of that sum.
Yes.
And so it's like the field quadratures are kind of the important thing for determining what your interference output is going to be.
Yeah.
So that's why it makes sense to talk about that. But you have to be able to go back and forth between both pictures. You got to be able to talk photons. And,
Right.
well, like all this stuff gets drawn as fields because
Yeah.
in the end, the way you detect phase is by doing interference.
Right. And the way that we, yeah, exactly, yeah. And the way that we think about how we use squeeze light very much depends on the phase of how you sync it up, and what quadrature you're squeezing determines what we see at the end. Yeah. Yeah, let's see, should we, I could either go through, okay, let me just finish this thing then, and then we will break. So again, like we were just talking about, there's the two things, right? There's the amplitude and phase of the field, equivalently the position and the momentum of a photon that pops in and out of existence, a vacuum photon fluctuation. And these two manifest pretty differently. Again, one is kind of this photon counting noise that per like root hertz, that is per any given second that you're measuring stuff, if you get a random extra photon, you have power fluctuations from that. That's photon shot noise, right? Again, the conjugate thing, photon momentum, how do we experience that? Because we have floppy mirrors, photons kick the mirror, mirror recoils, right? So these are how the two different quadratures of the field, that's how field amplitude fluctuations hurt us. They give us random kicks on our mirrors. That's how field phase fluctuations hurt us, is they lead to noise in our power measurement at any given second. That's shot noise and what we call quantum radiation pressure noise for amplitude momentum noise. Okay, let me get through these two and then we will stop. The shot noise problem is, I think, a pretty ubiquitous problem. people heard of shot noise? Like, are people familiar with this concept of photon shot noise? Yeah, okay. So shot noise, one way that you see shot noise in your everyday existence is just imagine trying to take a live photo, or imagine trying to take a video at night of somebody walking by. This is hard, right? Why is that hard? It's dark. That's exactly the problem that we face in squeezing. Why is it hard? Because it's dark. Why can't you turn up the exposure time, collect more photons?
Because the thing will move.
Because the thing will move. That's exactly it. Black hole signals move. So we cannot trivially expose an average for longer to collect more photons from our signal, right? It's dark, so we need to expose for longer. We need to measure an average for longer, right, to collect more photons. We inherently cannot do that because the signals are fast, because the source is moving, right? So this is a classic shot noise limited scenario. So if you think about this, like this is what's just on Wikipedia. You have a dark image. You're trying to take a nice photo, but it's dark. You could just expose it for longer and longer and longer, right, until you get more signals, but that doesn't work if you're measuring a fast signal, if you're trying to take a photo of somebody walking by in the dark. It won't work. This is shot noise. This is a very typical shot noise limited scenario. And now you can see, maybe appreciate a little bit why we always talk about the shot noise sensitivity per root hertz, right? That's saying what is our shot noise limit in every second of measurement time. That's how we want to talk about it for real-time sensing because, again, fast stuff. So the signal, if you expose longer, you get more signal photons. The shot noise only goes up as the root of the number of photons you're collecting because it's just counting noise. And so the signal-noise ratio improves as you have more photons. The next part is quantum radiation pressure noise. We talked about this already a little bit. Sorry, it's kind of a random order, but yeah, again, the mirrors are randomly kicked by vacuum fluctuations. Photon comes in, kicks the mirror recoils by some delta L in a given time window, right? You give it a velocity kick. After some delta T time, it has moved a little bit. That's position noise for your next measurement. And so that's exactly what you see. Amplitude fluctuations of the vacuum field lead to position fluctuations in your mirror. Then your next mirror photon comes, asks where is the mirror, gets the wrong answer, right? Because it's still recoiling from the first kick. That's quantum radiation pressure noise in a nutshell. And we use pretty extreme mitigation strategies already. For example, we use really heavy mirrors. Now that's why we have 40 kilogram, almost 90 pound glass mirrors, is exactly to suppress this problem so that that theoretical limit allows for detecting astrophysical objects. That's why our mirrors are so big. And obviously now we kind of use quantum sensing. And maybe this is a good place to end, is that these two come together, this back action quantum radiation pressure noise with this imprecision shot noise counting thing. There's a whole field in quantum sensing that's called quantum optomechanics. A lot of some of the origins, at least the initial motivation for thinking about quantum optomechanics was exactly the conundrum that LIGO is in, right? We want to measure where a mirror is, but every time we poke the mirror to measure where it is, the mirror moves. What happens if my second photon is like super close to my first photon? Will it have moved? No, right? Like if I probe super, super fast, mirror doesn't move, right? By the time the second photon gets there, because I'm measuring really, really fast. That's why the standard quantum limit is really low at high frequencies, because my subsequent photons are coming in really, really fast. Mirror hasn't moved, so it doesn't have a lot of displacement noise as a result of the photon kick at that frequency. If I kick it and I wait a second, and then my second photon comes in, say for a measurement frequency of 1 hertz when it's really slow, then my mirror is displaced a lot. There's a lot of position uncertainty in the subsequent measurement. That's why the standard quantum limit is very high at low frequencies. That's why there's this measurement time dependence of the standard quantum limit. And that's a statement that using standard laser light, you can never beat with standard laser light the standard quantum limit. But it's standard because it refers to standard laser light. If you're measuring something and it's moving, you'll always have some uncertainty related to the back action of the photon measurement. And this, that's all this is saying. If you calculate like the standard quantum limit for a mass of 40 kilograms, you see that this limit is at about the 2 to 10 to the minus 24 level at 100 hertz, which again, compared to that target number of 10 to the minus 21 strain, is at least compatible. Anyways, we can end this session here, but here's kind of how we get to the quantum limit. Maybe afterwards we can talk about how we go beyond the standard quantum limit by using non-standard quantum light for a squeeze vacuum.
All right. Let's thank our speaker.